Hello everyone, this is the fourth group from Division J from roll number 19 to 23 and I am roll number 20, the group leader of this group, and as you can see our topic is cache memory. So what we are going to cover in this video includes what is cache memory, then the location about the cache memory and working how cache memory works, further including levels of cache memory, followed by the types of cache mapping, which includes direct mapping, associative mapping, and set associative mapping, followed by the replacement algorithm of cache memory, also the writing into cache, which includes write through and write back. So first we will see what is cache memory. Cache memory is a type of computer memory that is used to store frequently accessed data for faster retrieval. It is a small and fast memory that is located between CPU and the main memory of a computer. Cache memory is a small and fast type of computer memory that is used to store frequently accessed data, and it acts as a buffer that helps to speed up the data accessed. The idea behind the cache memory is to reduce the time it takes to access data by keeping frequently accessed data in a small and fast memory, which can be accessed more quickly than the larger, slower main memory. When the CPU needs to access data, it first checks the cache memory. If the data is found in the cache, it can be retrieved quickly without having to access the slower main memory. If the data is not found in the cache, it is retrieved from the main memory and then stored in the cache for the future use. Cache memory is typically divided into different levels, with each level having a different capacity and access speed. The first level, that is L1 cache, is usually smallest and the fastest and built directly into the CPU itself. The second level, L2 cache, is typically larger and slower. It is located in separate chip. The third level, that is L3 cache, is even larger and smaller than L2 cache. It is usually located on the motherboard. So this all levels we will in detail we will see in the further slides. Overall, cache memory is an important component in modern computer architecture as it can significantly improve the performance of a computer by reducing the time it takes to access frequently used data. So now here we will see about the location of the cache memory. Uh, Cache memory can be located in different places depending on the types of cache and the architecture of the computer. Here are some common locations for cache memory. The first one is the CPU cache. The CPU cache is built directly into the CPU and is the fastest and smallest type of cache memory. It is divided into several levels, with L1 cache being the smallest and the fastest, and L2 and L3 cache being larger and slower. The second one is the chipset cache. Some computer architecture have a separate chipset that contains cache memory. This type of cache memory is located on the motherboard, close to the CPU. The next one, that is the disk cache. A disk cache is a type of cache memory that is used by the operating system to improve the performance of the disk input-output operations. It is usually located in RAM but can also be located on the hard disk itself. The next one is the web browser cache. Web browsers often have a cache memory that stores frequently accessed web pages and their associated files such as images and videos. This type of cache memory is usually located on the local hard drive of the computer. So, overall, the location of cache memory depends on the specific use case and the design of the computer architecture. However, regardless of its location, the purpose of cache memory remains the same: to improve the performance of the computer by storing frequently accessed data for the faster retrieval.
Hi everyone, my roll number is 90 and I am take over you further in this video. In our previous part, of our video, one of our group member talked about cache memory, what it is and where it is located in our computer system. So now we will be diving deeper into how cache memory works and what are the different types of cache memory. As a quick recap, cache memory is a small, fast memory that stores frequently used data for quick access. It is located between the CPU and the main memory, and it acts as a buffer between the two. So moving further towards working, let's understand first what is the need of cache memory. As we know, in our computer system, there are lots of programs are simultaneously running to perform our tasks on the PC. The performance of the PC depends upon how fastly and accurately the tasks are done by it, and this is depend upon the processor as well as the memory. Because the high-end CPU is ready to do tasks faster, but the memory is slower, so data reaches towards the CPU very slowly. That's why memory is equally responsible for speed of any PC. So now we going to compare the various memories present in our computer system with the microprocessor on the basis of their accessing speed. So the first memory we're going to compare is our ROM, which consisting SSD as well as HDD. Hard drive or nowadays SSDs, the speed of this memory is slow as compared to the CPU, which is around 80 to 160 Mbps for hard drive and 200 to 550 Mbps for the SSD. So this speed is very less as compared to the microprocessor. Microprocessor speed. The microprocessor speed is around 1 GHz to 3.8 GHz. So now you can see that how slow it. So to supply data faster to CPU, RAM comes in picture, whose access speed is greater than the main memory, which is 800 to 1600 MHz, but this is still lesser than the CPU. So to supply more data fastly to CPU, our hero of today's video came in picture, which is cache memory. The speed of cache memory is 10 to 100 times greater than the RAM. As level varies, the speed of the cache memory is also varies. Now let's take a look at how cache memory works. When the CPU needs the data to access, it first checks in the cache memory. If the data is not in the cache memory, the CPU has to go to all way to the main memory. This takes a longer time and slows down the overall performance of the system. So cache memory stores the programs which are visited recently and also stores the program previous or next of that program, which reduces the time of accessing the next requirement of the program for CPU. In this, the cache memory, the data transfer in the main memory to cache memory is in block format, and after that the data transfer from cache to CPU is in word. So the block consists of 128 words, and each word is of 4 bytes. So the memory transfer from main memory to cache is known as block transfer, and the memory transfer from cache to CPU is word transfer. The block transfer is very slow, and the word transfer is very fast. So moving further, there are levels of cache memories. The level 1 cache, it is also called as primary or internal cache. It is built directly into the processor chip. It has a small size from 2 KB to 128 KB. As it has small size, it has very high speed. Level 2 cache. It is slower than the L1 cache. Its storage capacity is from 500. Its storage capacity is from 512 kilobytes to 8 megabytes. Level 3 cache. Level 3 cache is separate from the processor chip. It exists on the computer that uses L2 advanced transfer cache. It is slower than L1 and L2 cache. The common size of this cache is up to 8 MB, and it is also greater than the 8 MB. So now let's see how the cache memory is working. So the cache memory works in our microprocessor. There are suppose you are taking an example of 4-core microprocessor that consisting cache level 1 memory. which is very fast, and it present in the cores of the processor. As you can see in picture, there are level 1 cache present in the cores of the microprocessor, and the data transfer is very fast, which is near to the speed of the microprocessor. And after that, if the data is not found in the level 1 cache, it tries for level 2 cache. Level 2 cache is outside the microprocessor. It is on the motherboard. After that, if the data is not found in level 2 cache, it tries for the level 3 cache, which also present on the microprocessor, which is not present on the microprocessor. It is present on the motherboard. Its size is also greater than the level 1 as well as level 2 cache, but its speed is very less as compared to level 1 and level 2 cache. If it didn't get data from level 3 cache also, it after that it last moves to RAM. If we do not get data, if the microprocessor do not found the data in cache, we call it as cache miss. And if microprocessor found the data in cache, we call it as cache hit. So that's how the different types of cache memories and the working of the cache memory. So further type of cache mapping like direct mapping, associative mapping, set associative mapping will be explained by my further group member.
Okay, now let us see the types of cache mapping. So the first one is direct mapping, second is associative mapping, and the third is set associative mapping. So let us see them one by one. Okay, now let us see the direct mapping. Direct mapping is the simplest cache mapping technique and it involves mapping each block of main memory to only one specific block in the cache memory. This is done by dividing the memory address into three parts: the tag, the index, and the offset. The tag identifies the memory block's location in the main memory, the index identifies the cache block's location, and the offset identifies the data position within the cache block. For example, if the cache has 16 block and the main memory has 256 block, the index will be of 4 bit. Direct mapping is easy to implement and it requires minimum hardware resources. However, it can cause cache conflicts, whereas two blocks in the main memory map to same block in the cache memory, resulting into reduced cache hits and increased cache misses. So this was one of the drawback of direct mapping. Now let us see what is associative mapping. So associative mapping is a more flexible mapping technique that allows any block of main memory to be mapped to any block in the cache memory. In the other words, each block in the cache memory can store any block from the main memory, and the mapping is determined dynamically based on the cache uses. To implement associative mapping, a special hardware called content addressable memory (CAM) is used, which can search the entire cache memory simultaneously to find the request data. Since the mapping is not predetermined, associative mapping offers a higher hit rate than direct mapping. However, associative mapping is more complex and it requires more hardware resources than direct mapping. Additionally, searching the entire cache memory for a block can be time consuming, resulting in longer access time. Okay, now let us see the set associative mapping. Set associative mapping is the hybrid cache mapping technique that combines the simplicity of direct mapping and the flexibility of associative mapping. That means it is a combination of both direct as well as associative mapping. In this technique, each block of the main memory is mapped to a set of blocks in the cache memory, and the mapping within this set is associative. For example, if the cache has 16 blocks and it is organized into four set of blocks, each block in the main memory will map to one of the four sets. Within each set, the mapping is associative, which means that any block from the main memory can be stored in any of the four blocks in the set. Set associative mapping offers a balance between simplicity and direct mapping and flexibility of associative mapping. It reduces the chances of cache conflicts while offering a higher hit rate than direct mapping. However, set associative mapping is more complex than direct mapping and requires more hardware resources. So, in conclusion, the choice of cache mapping technique depends on various factors such as the size of cache and main memory, cache access time, and the application specified requirements. Direct mapping is simple and efficient but cause cache conflicts, while associative mapping is flexible but it requires more hardware resources. Set associative mapping is a combination of both the two and offers a balance between the two.
Replacement algorithm of cache memory. When a cache memory is full and a new data atom needs to be added, the cache replacement algorithm decides which atom should be evicted from the cache to make space for a new atom. So here are some of the most common cache replacement algorithm. So the first is least recently used. This algorithm evicts the least recently used atom from the cache. It works on the assumption that if an atom hasn't been accessed for a while, it's unlikely to be accessed in the near future. The next is FIFO, that is first in, first out. This algorithm evicts the oldest atom from the cache. It works on the assumption that the atoms that have been in the cache the longest are the least likely to be needed in future. Next is least frequently used. This algorithm evicts the least frequently used atom from the cache. It works on the assumption that if an atom hasn't been accessed frequently, it's unlikely to be accessed in the near future. And the last is random. This algorithm evicts a random atom from the cache. It works on the assumption that all atoms in the cache have an equal chance of being needed. Writing into cache. The purpose of writing data into the cache memory first during a write operation is to improve performance by reducing the frequency of accessing the slower main memory or auxiliary memory. But this modification must eventually be synchronized with the main memory or auxiliary memory to ensure data consistency. So these two popular cache write policies are write through, write back.
As we mentioned earlier, these two popular cache write policies that are one is write through and second is write back. Write through is a storage method in which data is written into the cache and the corresponding main memory location at the same time. The cached data allows for fast retrieval on demand, while the same data in main memory ensures that nothing will get lost if a crash, power failure, or other system failure occurs. Although write-through minimizes the risk of data lost, every write operation must be done twice, and this takes time. The active application program must wait until each block of data has been written into both the main memory and the cache before starting the next operation. The data insurance, therefore, comes at the expense of system speed. Write-through is the preferred method of data storage in applications where data loss cannot be tolerated, such as banking and medical device control. In less critical application, and especially when data volume is large, an alternative method called write-back is used. Write-back is a storage method in which data is written into the cache every time a change occurs, but is written into the corresponding location in main memory only at specified intervals or under certain conditions. When a data location is updated in write-back mode, the data in cache is called fresh, and the corresponding data in main memory, which is no longer matches the data in cache, is called stale. If a request for stale data in main memory arrives from another application program, the cache controller updates the data in main memory before the application gets it. Moving further, write-back optimizes the system speed because it takes less time to write data into cache alone, as compared with writing the same data into both cache and the main memory. However, this speed comes with the risk of data loss in case of a crash or other adverse event. Write-back is a preferred method of data storage in application where occasional data loss event can be tolerated.